Thank you, Mr. Vishnu. Good evening, the session chairman. Good evening to ladies and gentlemen. I'm from Exide, and you may have heard of us that we have been in the business of providing batteries, energy storage systems for last 70, 75 years. And even though we are primarily known as the manufacturers of the lead-acid battery technology, you may also have read in the newspapers and other what you may say, the trade journals, that we are now venturing into the other chemistries also, which includes lithium ion, which is already addressed, which is already advertised. And we are looking into some of the other options too. Now, my time has been limited to 20 minutes, so I will be basically just touching upon the overall, what you may say, some of the major highlights of the different energy storage systems which are today conventionally available in the market and manufactured, some of them by us. I would like to share this presentation with organizers of this conference, and this might be distributed. And I'll be very happy if questions are asked or mailed to me subsequently. So with that, let me come quickly to the main subject. And I don't think with experts like you around, I need to emphasize that electrical energy is a rare example of a product that ideally should be consumed at the instant it is generated. Because the moment we talk of storage of electrical energy, it becomes a technical challenge. And the technical challenge comes from a number of points. It comes from the storage efficiency. It comes from the vulnerability or the relative sensitivity of the storage device to various operational parameters. The sensitivity comes from the fact that the storage devices efficiencies tend to age pretty fast. So all these things are taken together. So, but generally, if you look at electricity storage schemes, then it can be mechanical, like the pumped hydro. I'm very glad that after my presentation, there's a presentation on pumped hydro. Then it can be simple direct electrical storage like capacitors. Then it can be chemical, hydrogen, much of is being talked about hydrogen these days, thermal. And finally, of course, the electrochemical systems, the most notable of them being lead acid and lithium ion. Just to give you an overall idea of where we stand insofar as these are concerned, you will find that the mechanical systems, like the pumped hydro, the compressed air, which are right at the top, are for the real bulk storage, where we are talking of storage of the order of hundreds of megawatt and maybe with backups running into hours. And at the lowest end, you will find the supercapacitors and etc., where it might be for a sharp delivery of power for a very small, maybe few seconds of time. So right at the top, you have the mechanical, at the bottom, you have the electrical, and in between, you have all the different chemistries which come into the storage of electricity. Now, when we talk of an electrochemical reaction, when we talk of an electrochemistry, basically, please understand that all we are trying to do is to have a pair of metal rods, which we call electrodes, which can be immersed in an electrolyte, and the anode should be so thermodynamically positioned that it delivers spontaneously electrons to the outer circuit. The moment you can have this configuration, you can have an electrochemical cell, and a collection of electrochemical cell forms what is known as a battery. Now, this is a typical schematic of an electrochemical reaction system inside a cell. I will just draw your attention to two cases. This is a typical case where electrons are released through electrochemical reactions of the reactants, most commonly the lead dioxide, dissolving into the electrolyte, reacting with the sulfuric acid, and again reprecipitating. This requires a physical dissolution, reaction, and a precipitation. Now, on the other hand, if I look at a typical arrangement in what is known as a rocking chair mechanism, which is a lithium ion battery, here the ions are basically traveling without any reaction in between electrodes and getting placed in the interstices of the opposite electrode. So again, once again, if I start, the electrons are released. There's no electrochemical reaction taking place. It's just migrating through the electrolyte and depositing in the interstices of the material of the positive electrode. Why I decided to show you these two is for a simple reason. This highlights some of the basic features which are much discussed amongst all of you whenever you are deciding on which chemistry to choose for a particular storage activity. I am comparing a lead-acid battery and a lithium-ion battery. In a lead-acid battery, the power is generated through an internal electrochemical reaction, which involves a dissolution, electrochemical reaction, and a precipitation. This requires time. And hence, a lead-acid battery, particularly when you are charging, doesn't charge as fast as a lithium, because in the lithium, there is no such steps like dissolution, reaction, then precipitation. It is just a mechanical translation of the ions through the space in between the electrodes, and therefore can be much, much faster. This gives lithium ion certain outstanding advantages, like it charges very fast. Its discharge characteristics are also pretty fast, though that honestly with the lead acid also is pretty good. And also, very importantly, the charging efficiencies are much better in the case of a lithium ion. Now, having said that, do we therefore look at what are the options that we have? Where intentionally I have shown you a huge tree of electrochemical energy storage and conversion systems. And given the time that has been allocated to me, I can only touch through some of the major parts of it. I leave the electrochemical battery, which are at the center. I look at the two other ones, which are at the top. On one hand, you have the fuel cells. I'll spend a minute or two on fuel cells later, because that is increasingly becoming very important for specific applications where we are talking of bulk, what you may say, transportation. We are talking of industrial applications. And on the other hand, we are talking of the electrochemical capacitors, where the power requirement is for a very brief period of time, for a very short period of time. Excuse me. However, the capacitors have a very important feature that it allows the capacitor to be charged at an extremely fast rate. So if you are generating energy in sudden bursts, capacitors will be pretty good to trap that. But obviously, as you know, it cannot hold on to the charge for long, nor can it take a deep discharge, which means a longer energy charge and discharge. Coming at the center, we talk of the batteries. We divide the batteries again into two. We talk of the rechargeable batteries, and we talk of the flow batteries. Flow batteries are also, of course, rechargeable, but the mechanisms are different. We'll talk about the flow batteries also a little bit. In the rechargeable battery, we have the lead acid family, we have the nickel family, we have certain special products like zinc halogen, we have talk of the sodium sulfur. These are the ones which are commonly used for energy storage. A new class which is emerging and becoming quite important is a metal layer, and of course, the lithium ion. So we look at some of the family. We start with lead acid. As I work for Exide, and Exide for the last 75 years has been primarily a lead acid manufacturer. We'll talk about the lead acid first. This is just a summary for the different chemistries which I've just mentioned to you. And as you can see, lead acid has a very limited specific energy. not more than 25 to 40 watt hours per kg. Typically, maximum it can go up to 40 to 50 watt hour per kg. Some of the latest versions, you may have heard of the bipolar configuration, may take it to 60 to 70 watt hours per kg, whereas a lithium ion typically starts around 120, 130 watt hour per kg and can go up to as high as even close to 300 watt hours per kg. Coming to the lead acid battery usage for energy storage applications globally, we would just like to highlight a few versions which are today available commercially and are being deployed commercially across the world, and where we are basically talking of energy storage, where we are looking at the battery as an energy bucket, where typical shifting type of application or peak load management, where batteries can be used, typical lead acid can also serve a cycle life of as much as 3,000, delivering a lifetime of 14 to 17 years easily. Some of the major versions which are available in the global market are the ones which are marketed by Hitachi as well as by Furukawa. Exide, we have also developed this high cycle life, long life energy storage batteries in the lead acid configuration. We are being modest. We are talking of a service life of 10 years and a cycle life which might go up to 4,000 to 4,200 cycles at 70% depth, which is as close as you can get to lead acid, to lithium. There are further developments in lead acid. We are now talking of a new technology known as ultra battery. I was mentioning to you about capacitors. Now, if you can have internally constructed lead acid battery where the electrode can double also as a capacitor electrode, then you can have a battery which can charge at extremely high rate. Under such circumstances, a lead acid battery can deliver the performance of a lithium ion battery for a very high power charge and discharge. So these are certain new versions which are coming into the market. They can be very well suited for energy storage applications, including high power charge and discharge, when we are talking of frequency response or voltage balance and such applications. There are certain weaknesses. They are better suited for high power cycles. They're also dependent on an electronic management system. Nickel cadmium is a battery which all of you are familiar, but people have moved across nickel cadmium because of environmental and other issues. In the nickel family, perhaps the most promising candidate in our energy storage applications is nickel iron. This is again a very old technology which has been developed 50, 60 years back. And this is a product which is extremely robust, which can handle a lot of abuse. And this is very critical in terms of both overcharge and particularly over discharge. But it can deliver an extremely long cycle life. So this has also been there, but it has been more plagued with manufacturing issues. So it has never become very popular. Now, flow battery is a very interesting consideration where the basic electrodes are in the liquid form. And the electrode materials under the liquid form, they are pumped from two individual tanks, put into a electrode where they electrochemically react. And as I told you, they release the electrons which go into the external circuit. One of the major advantages of the flow batteries is, of course, that you can completely segregate power and energy, because power comes from the total dimensions of the electrodes and total energy comes from the volume of the reactants in the tank. So if you just want to increase the power without changing the energy, you can increase the membranes of the electrodes in between. Or if you want a higher energy throughput, you just need to replace it with larger tanks. However, this has certain weaknesses, complicated in comparison with standard batteries, because it requires pumps, sensors, so maintenance becomes an issue. It also has a poor energy to volume ratio. Aluminum air is another technology which is being much discussed, but this is not really a rechargeable battery. It's more a primary battery, where the aluminum reacts with the oxygen, gets oxidized, and over a period of time, gets completely chemically converted. And at that time, the electrode has to be replaced with a fresh aluminum electrode, and this cycle can go on. However, the main advantage of this is its extremely high energy density because of the very low weight of aluminum. There are many other metal air batteries, all of which basically function on the principle of the redox reaction taking place inside. So you will keep hearing every now and then the success of magnesium air, silicon air, and other applications. Sodium sulfur is a technology which some of you might be familiar, where we are talking of bulk storage of 30, 40, 50 megawatt hours, where there are certain vulnerabilities because this is a very high temperature application where the electrolyte or the battery has to be kept at temperatures as high as 300 to 350. But under that circumstance, it's an extremely robust system with a very high efficiency, as well as very low, what you may say, self-discharge and other features. So there is a risk in it because it's a very high temperature, but it's common. It has been deployed across the world. There have been some minor issues which have been mostly coming from the high temperature, but it's an option available to you. Finally, we come to the lithium ion. Lithium ion, I've already explained to you, is basically where the entire generation or the production of energy inside the system is dictated by the shuttling of the lithium ion between the positive and the negative electrodes. And this can take place at extremely fast rates. However, certain caution will have to be maintained because it has otherwise some ramifications in terms of its safety. So typically, some of the very common features are the versions that we are known to all, the NMC, where we talk of the cathode material, lithium compound, which has also nickel, manganese, and cobalt. It can be lithium iron phosphate. Now, if you're talking of lithium, manganese, cobalt, you can get very high energy density, but also very high cycle life, even up to 4,000 or 5,000 cycles, but may not get the safety and the other features that you get in a lithium iron phosphate, which has a lower energy density, somewhere in the range of 120 to 140 watt hours per kg, but will give a much more stable performance. And typically, it's a more preferred version for energy storage application from the safety point of view. So, as I told you, the cathode is the different lithium compounds. The anode is mostly graphite, but can also be other lithium metal alloys or iridium lithium titanate, which acts as the LTO, which has an extremely high cycle life. Now, electrolyte is one of the major things because normally it uses an organic electrolyte, and that is sometimes the root of most of the safety issues that we hear across the world. It can also be a polymer electrolyte, and the future perhaps belongs to the solid state electrolyte, towards which we guess that in another 3 to 5 years, the world will have most of the safety issues of the lithium largely addressed. So these are some of the features I have already mentioned. It has extremely high energy density. It charges at pretty fast rate. It doesn't necessarily have to charge in 1 hour, at least in energy storage application. A modest current of 30% or 40% can charge it in 2 to 3 hours. It is extremely flat in terms of its energy deliverable even at high rates. It can deliver a very high cycle life. The weakness, as usual, we talk of the safety. Its strong dependence on electronic management devices and other things. Fuel cells, again, fuel cell is not a battery. It requires pure hydrogen. Hydrogen can be generated green through renewable sources and then stored and then be supplied to a processor in which the fuel or hydrogen can be burnt or oxidized to form water and energy can be generated. So this is a technology on which a lot of people are betting for the long term. I finally go out of these various chemistries and leave it up to you to ask me questions now or later, and just sign off by just talking of a few parameters which we as battery designers have always considered to be important for you to take care when you're doing a system design. We'll mention a few points about the comparison of lead acid and lithium ion battery, but we can extend the table for the other chemistries also. Now, whenever we are doing sizing of a lead acid battery, we have a pretty standard aging factor, which is as per the international, what you may say, guidelines, even standardized in IEEE. Whenever we are sizing a particular battery for a particular load, we use aging factor of 1.25. In lithium ion battery, this is something which is not as yet standardized. So this is somewhere we would like to address user forums like you to push the manufacturers to come into a common base. When we talk of safety, one of the features of lead acid battery is it is intrinsically safe. It doesn't have anything inside which can cause a fire or an explosion. There are situations